Welcome all. Today we will look into acceleration diagram and some problems related to acceleration diagram. Here is the first question. The crank of a slider crank mechanism rotates clockwise at a constant speed of 300 rpm. The crank is 150 mm and the connecting rod is 600 mm long. Determine 1. Linear velocity and acceleration of the midpoint of the connecting rod, and 2. Angular velocity and angular acceleration of the connecting rod at a crank angle of 45 degree from inner dead center position. And these are the given data. Number of rotation of link BO. Here that link is the crank of the slider crank mechanism. That's equal to 300 rpm given. Then omega is equal to 2 pi n by 60, where n is the rpm. Then 2 pi into 300 by 60, that's equal to 31.42 radians per second. OB is equal to 150 mm given in the question. That length is given in the question. That's equal to 0.15 meter. BA is equal to 600 mm. That's equal to 0.6 meter. Then linear velocity of this point B with respect to O is equal to linear velocity of point B with respect to O is equal to omega BO, angular velocity of BO, link BO into OB. OB is the length of the that crank. That's equal to 4.713 meter per second. We have already derived this equation. Linear velocity is equal to omega into R, where R is the distance of the particular point where the velocity is calculating to the pivot point. R is the distance between this particular point where we calculating the velocity and the pivot point between these two points. Okay, then first we have to draw the velocity diagram. For this purpose, we have to draw the space diagram first. To draw the space diagram, here first to draw the horizontal line, then that particular angle 45 degrees given, which the angle between this crank and the horizontal line, that is given as 45 degree. Then that length is equal to 150 mm. We can take any suitable scale to represent that length OB. And after that we can draw this connecting rod. That length is also given. We can draw an arc with radius is equal to 600 and the center is equal to point B, and find out the that intersecting point that will become the point A. Then we can easily complete this space diagram. Then the velocity diagram. Here we can draw this velocity diagram by taking a suitable scale to represent the velocity. Okay, first we have already calculated the velocity of B with respect to O. Velocity of B with respect to O. That velocity is equal to V with respect to O is equal to absolute velocity of B, because that point O is the pivot point, and that is at the rest. So we can say that VBO is equal to VB. That's equal to 4.713 meter per second. We have already calculated this value. Then we know this velocity. This velocity is velocity of B with respect to O, and that is perpendicular to link BO. So that we can draw the velocity of B with respect to O. We have already calculated the magnitude of that velocity and direction. We know that that direction must be perpendicular to link OB. Then we can draw this line OB having length is equal to 4.713 meter per second. We can take any convenient scale to represent this value. Okay, and that length we have already calculated this magnitude and direction. This direction must be perpendicular to this link OB. We have already drawn the space diagram. Then we can draw OB length OB that must be perpendicular to link OB. For this purpose, we have to fix the fixed points. Here, fixed point means pivot point. Here, fixed point, this point O. We can first specify that fixed point by a small letter O. Then we can draw OB. That OB length already calculated that length. Then that direction must be perpendicular to this. We can draw a line which is perpendicular to this particular link. This line must be perpendicular to this link. Then we can easily draw the vector VB. Then from point B, we can draw a line which is perpendicular to link AB, That line, in that line, we can represent the velocity of A with respect to B. We know that the velocity of A with respect to B, that must be equal to omega AB into AB. But the value of omega AB is unknown in this particular case, so we cannot calculate the velocity of AB. But the direction of velocity, this velocity is always perpendicular to link AB. That is a known factor. Then we can draw a line through B which is perpendicular to AB, we can easily draw that line. That will be the line of action of velocity of AB. But magnitude is unknown. This length BA is unknown. Then the third velocity of A, velocity of this slider with respect to O. O means this fixed link O. The velocity of A slider with respect to O. Velocity of slider A with respect to O is equal to velocity of slider, because that point O is stationary. Then that VA must be along horizontal direction. That is a constrained motion, because slider can only move in the horizontal direction. Then we have already know the velocity is along horizontal direction. Then we can draw a straight line. Horizontal line passing through O. But again, this value VA, the magnitude of VA is unknown. Then the intersecting point of this particular line and this particular line intersect at point A. Then we can say that the length AB, or this length AB is velocity of A with respect to B. Then this length OA, small letter OA will become, that vector will become velocity of A with respect to O. We can measure this value, and that value will become 4 meter per second, and VAB is equal to 3.4 meter per second. We can multiply this length into scale. We can choose any convenient scale to draw this particular velocity diagram. Then finally, in order to find the velocity of midpoint D, the velocity of midpoint D of connecting rod AB, divide the vector BA, small letter, divide this vector BA, small letter BA, in the same ratio as capital D. Capital D divides AB. Capital D divides AB. Capital AB. Then BD divided by BA. This BD divided, small letter BD divided by BA must be equal to capital BD by BA. That means same ratio must keep in this particular space diagram and also in the velocity diagram. Then BD by BA, small letter BD by small letter BA must be equal to capital BD by capital BA. Then we can find out this small letter D. Then length OD, small letter OD, connect that particular point, small letter D, with this particular point O. Then we can measure OD, vector OD. That vector OD will become the velocity of D with respect to O, or simply VD, because again this point O is at rest, or O is a stationary point. So we can say that velocity of D with respect to O is equal to absolute velocity of D. That will become 4.1 meter per second. 4.1 meter per second. That's all about the velocity diagram. Okay. And this is the final answer. First figure is the space diagram, and the second figure is the velocity diagram. Then after drawing this velocity diagram, we can draw the acceleration diagram. Here this link crank is OB, crank is OB, and crank has a constant angular velocity omega, constant angular velocity omega. That means d omega by dt is equal to alpha is equal to 0. Alpha means angular acceleration. For a constant angular velocity, this angular acceleration will become 0. That means d omega by dt is equal to alpha. That must be equal to 0 in this particular case. Here we know that the radial component of acceleration is equal to v square by r, and tangential component of acceleration is equal to alpha into r. Then for this particular link OB, that tangential component is equal to alpha into r, that's equal to 0, because alpha is already found out that alpha is equal to 0. Then the total acceleration is equal to the vector sum of radial component and tangential component. If this tangential component is equal to 0, then total acceleration must be equal to this radial acceleration only, radial acceleration itself. Then that acceleration of B with respect to O is equal to this radial component of acceleration of B with respect to O, that's equal to V square by R. V square by R, that's equal to V. We have already found out that V as 4.713, that square divided by that length is equal to 0.15. That's equal to 148.1 meter per second square. Then in the next step, radial component of acceleration of A with respect to B. Here that link is this one, B and A. AB is the connecting rod. Then radial component of acceleration of A or B. Acceleration of B with respect to A, or acceleration of A with respect to B. That radial component is equal to V square divided by BA. V square of A, that means VAB whole square divided by BA. We have already derived this we have already found out that the velocity of A with respect to B, velocity of A with respect to B, that's equal to 3.4. Then radial component of acceleration of AB is equal to 3.4 whole square divided by 0.6, that's equal to 19.3 meter per second square. Then we can draw the acceleration diagram like this. First, we can fix the fixed point O. We can fix that fixed point O as O dash. In acceleration diagram, we can represent that point as O dash. Then acceleration of B with respect to O. That's a radial component of acceleration of B with respect to O. That's the complete acceleration or acceleration of B with respect to O. That is in the radial direction. That means that must be along link BO. Along link BO, then we can represent that magnitude. That magnitude in this particular direction. That is equal to this one. We can take any convenient scale to represent. There is no tangential acceleration. So we can name this point, this end point as B dash, B dash. That means acceleration of B with respect to O is represented by B dash O dash. That must be along BO, along BO. Okay, next we can represent the radial component of acceleration of A with respect to B. That value, that magnitude is already found out, and that must be along radial component must be along AB. Along AB, we can represent that length. We can represent that length as B dash X. B dash X. That must be parallel to AB. That must be parallel to AB. This line must be parallel to this line, and that length is already found out. Then we can draw the tangential component of acceleration of A with respect to B, and the tangential component must be perpendicular to this radial component, or that tangential component must be perpendicular to this link AB. But we can't find out that value of that magnitude of tangential component of acceleration of A with respect to B, because this value is equal to alpha into R. We can't find out alpha. We can't find out alpha before we can draw this acceleration diagram. Then we can draw this dotted line which is perpendicular to AB, but we can't fix this point A dash. We can draw a straight line, dotted line in that particular direction. Then in the next step, the acceleration of A, again acceleration of A with respect to O. Acceleration of A with respect to O. That's again the complete acceleration of A. Complete acceleration of A. The radial component of we have discussed these two steps already. Then now from O dash, draw a vector O dash A dash parallel to the path of motion of A. That is the acceleration of A. We have already said that acceleration of A with respect to O must be equal to complete acceleration of A. The direction must be along horizontal direction, so that we can draw the acceleration of A in the horizontal direction, which is passing through this particular point O, so that we can draw this particular line. Then the acceleration of this we can find out this point A dash as this particular, the intersecting point of this line, this particular line and this particular line, because this point, when this point is A dash, we can say that this particular line is the acceleration of A with respect to O, and again this line as x tangential component of acceleration of A with respect to B. This intersecting point must be equal to A dash. Or we can say that the resultant of this radial component and tangential component, that's equal to this line, this particular thick line. This thick line must be the closing side of the triangle, closing side of this particular triangle. Then if this is the resultant of radial component and tangential component, then this point will become A dash. That means this is the complete acceleration of complete acceleration of A with respect to B. That means this particular point will become A dash. This particular point will become A dash. Then we can find out this value of this one. We can measure this length into the scale taken, and we can also measure this A dash B dash length. Then again, in order to find the acceleration of the midpoint of the connecting rod, again B dash D dash divided by B dash A dash. The ratio of the distance in the acceleration diagram. B dash D dash divided by B dash A dash must be equal to BD by BA. BD by BA, that is the ratio of distances in the space diagram. Then we can find out this point D dash by using this particular ratio. Then connect D dash and O dash. We can find out the value of acceleration of D with respect to O, or absolute acceleration. By measuring O dash D dash, we can say that acceleration is equal to 117 meter per second square. 117 meter per second square. Then the angular velocity of the connecting rod. Next portion, the angular velocity of the connecting rod. We know that the velocity of the connecting rod, velocity of A with respect to B, is equal to omega AB into AB. We have already found out this VAB. Then we have already know that the length of AB. Then by using this equation, we can easily calculate omega AB. Omega AB is equal to VAB divided by BA. That's equal to 5.67 radian per second square. Then finally, the angular acceleration of the connecting rod, alpha AB. Alpha AB. We have already know that tangential acceleration of AB is equal to alpha AB into AB. Alpha AB into AB. We can find out, or we can measure this length A dash X. That length is equal to 103 meter per second. This length is equal to 103 meter per second. That length into scale. Okay. Then we know that alpha AB is equal to tangential component of acceleration of A with respect to B divided by BA. Then we can calculate that value as 171.67 radian per second square. Okay. That is answer. Thank you. Thank you all.